This video is on the Hill model of muscle contraction, and it will also cover the difference between isometric and isotonic contractions. So the Hill model is basically an engineering diagram used to sort of simplify the components involved in the contraction and lengthening dynamics of striated muscle. And so it looks a bit like this. It has three main components. We add those components and then we'll explain them. So in one of those components, a very simplified view of a sarcomere. Doesn't matter really how many pieces of it we show here. Hopefully that looks a little bit like the sarcomere you've seen before. And so that's going to be one element. And then we have, in line with that, another element. And a final component over here. Okay, so what is all this supposed to mean? So first of all, what you could do is you could visualize this as sitting within the muscle belly if you wanted to, and these sort of being the tendons or the connections to the bone at the end here, right? And again, it's Hill model here. So force, when the sarcomeres contract in a muscle collectively, right, whether it's some of them or all of them, when they contract, they're going to pull the ends of on the ends of the muscle, right? So force that's generated is pulling this way on, right? I'll put a B out here for, in most cases, bone attachments, right? We're going to pull on our bones, right? Pull them, right? You want to pull your radius towards your humerus, right? We have a muscle that contracts to pull those two closer together, right? Or at least in that case, decrease the angle between them. And the components here have labels, and so we'll put those on. So the CE is the contractile element. The SEE is the series elastic element. And then the PEE is the parallel elastic element. And we'll say the least about the parallel elastic element. I'll tell you more about its role than like what its components are. We already know what the components of the contractile element are, right? Those are the thick and thin filaments of the sarcomeres. They're the tension, it's the tension generating component. When those are stimulated, so you can think about, right, put this in context, you can think about the excitation contraction coupling mechanism, you know, calcium release, action potentials, calcium release, binding to troponin, moving tropomyosin, the myosin head, binding the thin filament, ATP turnover, and then shortening of, and again, I have a single sarcomere here as our entire, representing the entire contractile component of the muscle. In other words, all of the sarcomeres. But so the Z lines would be pulled together, and this would shorten when stimulated, right? So anytime we generate tension, right, the thick filament is going to pull on the thin filament. Now, you would assume that that means that the sarcomeres would always shorten. And that is actually not always true. So this is why we have to explain this idea of what is an isotonic versus what is an isometric contraction. And then actually a subtype of isotonic contraction. But leave that aside for the moment. When the contractile element is pulling, and again, we could assume it's shortening for the moment. If it's pulling, then it is going to pull on this series elastic element. In other words, your attachment to bones are out here, and the series elastic, series means in line with, so the contractile element pulls on this element before it can pull on the bone, right? It has to stretch this part before it will effectively pull on this part. So you can think of this as like a rubber band, if you want, or a spring that needs to be sort of stretched before we can generate real tension out here. And this is where the terms internal and external tension come in at least in my textbook. Because internal tension is generated here, and external tension is generated on tendons and bones. And to get external tension, we have to stretch the series elastic element. And again, it's one of the reasons that individual twitches don't do much. They're so short-lived, fractions of a second long, is that most of that energy goes into stretching this rather than pulling on bones. So, with that said, when we have basically the two big categories of muscle contraction are isotonic and isometric. And iso means same, tonic means tone, or if you prefer, tension. And isometric means same length, right? So in an iso, we'll do the easier one first. And actually, to back up before I get into that, most movements require components of both isometric and isotonic contraction, right? If you think about it, if you go to pick up a heavy book bag, right, or suitcase, right, when you first go to pick it up, you start to generate tension before it comes off the ground. So in other words, your arm does not bend initially. You're generating tension, but the weight has not moved. So that is called, right, so if the weight has not moved, then we haven't changed length, and the tension you're generating is during what's called an isometric contraction, right? The length is not changing. So in that scenario, what's going to happen is the ends are not moving yet. This is going to contract. This is going to shorten, right? But because the ends aren't moving, if this shortens, then this has to do what? Get longer, right? And that makes sense, right? The contractile element has to pull on the series elastic element before it can pull on bones. And the series elastic element is things like the connective tissues within muscle, the costomeres, those connections between the internal contractile components, right, the myofibrils and all of their protein filaments, and the external connective tissues, right? There has to be a portion, it's made of proteins, but a link between, the tension generated by sarcomeres inside the cell and tension on the connective tissues that are outside the cell, right? Tendons are not tied to things inside the cell directly. The tendons are not embedded in the cells. The tendons are attached to the connective tissues that surround the cells. And so to get tension on the inside to be conveyed to the outside, we have to have something that spans the membrane and conveys that tension. That's called the costomere. And it's just that series of proteins that sort of span from myofibrils inside the cell, sarcomeres within the myofibrils inside the cell, to the connective tissues outside the cell. So anyway, in an isometric contraction, again, think about picking up that heavy bag, right? Initially, you're generating pull, but it's not coming off the ground yet. So action potentials, right? Calcium, all the stuff we said a minute ago. We're going to get shortening here, which means we're going to get stretching here, right? We're going to generate force on the ends, but when it's isometric, we have not exceeded the load, right? There's your definition. An isometric contraction is one in which the tension generated does not exceed the load, the thing you're trying to move, and the muscle length does not shorten. Okay? That's isometric. Now, so now you're like, it's heavier than I thought, the bag. And you try a little harder, and all of a sudden, so add in the components that you're required to do that. You'd have to get more motor unit recruitment, more wave summation and tetanus of the motor units that you're recruiting. more tension generated, all right? So more sarcomeres being involved. And now you're going to have greater tension generated by the contractile elements. You're still going to be stretching this series elastic element, right? That hasn't stopped. But now the force you generate is going to exceed the load, right? So now all of a sudden, right, you can't see my arm, but now all of a sudden what you're trying to pick up comes off the ground, right? And you're able to lift it. So now the ends of the muscle are going to come in because we're pulling the bones closer together, right? Or changing the angle at least. And so we're shortening, right, our muscle overall. And so that is called an isotonic contraction. Now, think about the bag you're lifting. If the bag you're lifting weighs 20 pounds, well, if you're in this position or this position or this position, it weighs 20 pounds, right? And so the tone, the amount of tension you need to generate stays about the same during the whole movement, right? Because it's 20 pounds throughout the whole range of the movement. There's mechanical advantages by different angles and things like that. But if that's fixed, right, the weight is 20 pounds and it doesn't change. And so the tone in the muscle to lift it has to be 20 plus, more than 20 pounds of force. And so it's now isotonic. But there's two versions of isotonic. Because the muscle is shortening, right? So the whole hill model is going to look like this now. All right, now look at where my thick filaments are now. See the red guys? All right. The thick filaments haven't changed length. I'm trying to keep them the same length. Right? Our series elastic has tension on it because this guy is pulling on it, right? The contractile element is pulling on it. So we're going to make this look like it's more stretched now. All right. But remember, my ends have to come in, so I want to stop that a little bit short here. And what happened to my... Right? Yep, I got both my ends kind of coming in there. So the whole thing overall is shortened. What happened to my parallel elastic element? Right? It got squished. Right? So the parallel elastic element, you got to think of that as sort of like a rigid spring. Right? It has to be compressed when we shorten, and it has to be stretched when we lengthen. So it tends to just sort of oppose changes in length. And it's not intentionally there. It's just part of the structure of the muscle and the connective tissues, right? And so to draw that, we're going to make it look like it's more squished together now. Right? Something like that. Sort of squashed a little bit. Okay, so that was to get to this contraction, to this position, new position, we had to undergo isotonic concentric contraction, right? Shortened, stretched, compressed, right? All right, so now you've lifted your bag and now you're just holding it there, right? Well, guess what? Now we're in this static position, right? Remember, the transition from here to here was your isotonic concentric. Once you're here and you're just holding your bag, right? Now you are once again isometric. You're just isometric in a new position, a new degree of shortening. Now, if we want to put the bag down, right? Well, we want to put the bag down, we have to reduce the tension. Well, you could just reduce all of the tension, right? Of course, you just drop it, right? And so this would relax, right? This pull on the series elastic would go down, and the whole thing would just get lengthened by the load on the arm. Well, let's not use the just shut off the muscle example. Let's say you want to not drop your bag, but lower your bag. Right? And so to lower the bag, you need to generate less tension in the muscle than the load there and than the load on the muscle, right? So again, the bag weighs 20 pounds. We need to reduce the tension development to less than 20 pounds of force for it to be lowered. Well, in that scenario, though, are we still forming cross bridges? Yes, right? Because you're still generating tension. Cross bridges are the root source of tension development. But our sarcomere isn't shortening. The sarcomeres are not shortening as the muscle lengthens, right? And again, we're lowering it, and it's still almost 20 pounds of force. So it's still isotonic, right? We didn't just like drop it, right? We're still just lowering it slowly. So it's essentially still almost exactly 20 pounds of force, but not quite, right? So it's still isotonic, but now the muscle is getting longer. Well, that's an isotonic eccentric contraction, right? So again, isometric, let's review them all. Isometric was when the load and the load exceeded the tension developed by the muscle, and the muscle doesn't shorten. You can do isometric contractions very easily. Put your two hands together like this and push, right? You can generate all kinds of muscle tension, right, in your shoulders and your chest. There's no movement, right? You're generating force. You're getting, the contraction of the sarcomeres, stretching of the series elastic, but the overall position of the bones isn't moving, right? Let's lift the weight now, right? In isotonic concentric, the tension generated by the muscle exceeds the load and the muscle shortens, right? That's isotonic concentric. And then when we lower the weight, right, we still have almost, again, under control, we still have essentially the same tension developed as the load, right? Just a hair less. So it's still isotonic. But now the muscle is lengthening, so it's isotonic eccentric. So in isotonic eccentric, the tone is, tension developed is constant, right? Ever so slightly less than the load. The tension developed is constant and is less than the load, right? When it was concentric, the tension developed was greater than the load, shortening the muscle. In eccentric, the tension developed is slightly less than the load, yet constant, and the weight will go down, i.e. the muscle will lengthen, right? And of course, our Hill model here would get extended, right, as we undergo isotonic eccentric contraction, right? Because we would be lengthening this while generating tension, still generating the tension, right? Again, if you lower something under control, you still are generating, effort to activate motor units to generate cross bridges. But you have to think of it as like losing a tug of war, right? You're still generating tension on the rope, but the rope's sort of slipping through your hands. That's what's happening between the thick and thin filaments in isotonic eccentric contraction.